The greatest misunderstandings in physics. Today we're discussing Schrödinger's cat. We're going to learn what Schrödinger was actually telling us. Most people know Erwin Schrödinger for one thing: the cat. The famous cat that is somehow alive and dead at the same time. The cat became so famous that almost nobody remembers what Schrödinger was actually saying. Which is ironic, because the cat was never the discovery. The cat was the complaint. Schrödinger created the thought experiment to expose what he saw as a problem in the emerging interpretation of quantum mechanics. And get this: Schrödinger never thought the cat was both alive and dead. That was the entire point. He thought that conclusion was absurd. To understand why, we have to go back to the beginning. In the 1920s, physicists were uncovering something extraordinary. The deeper they looked into nature, the less it behaved like a collection of tiny objects moving through empty space. What appeared instead were waves, interference patterns, resonance, standing structures, relationships, phase. Schrödinger responded by developing one of the most important equations ever written. It's simply called the Schrödinger equation. Today, it is often introduced as the foundation of quantum probability. That is not how Schrödinger understood it, nor is it what the mathematics itself reveals. His equation describes the continuous evolution of a complex field. Smooth, governed by phase, and importantly, entirely deterministic. The field evolves, the phase evolves, the structure evolves. Nothing in the equation itself is probabilistic. Then came Max Born. Born proposed that the wave function should not be understood as a physical field. Instead, he suggested that its magnitude describes the probability of finding a particle in a particular location. Remember that emphasis on magnitude. It becomes important later. This became known as the Born rule. The rule worked. Its predictions were extraordinarily successful. The interpretation spread rapidly. The Copenhagen interpretation followed. Probability moved to the center of the story. Measurement became mysterious. Particles returned to the throne. And one of the most profound phase equations ever written became widely taught as a machine for predicting random outcomes. Probability entered through interpretation. The phase evolution remained exactly where Schrödinger had placed it. Schrödinger never fully accepted that move. This is where the famous cat enters the story. Schrödinger postulated the cat as a reductio ad absurdum to demonstrate that something had gone off the rails in the mainstream interpretation of quantum mechanics. Basically, he was trolling the scientific community. Einstein fully agreed. Popular culture often portrays Einstein as an old man refusing to keep up with the modern physics. The historical record tells a different story. Einstein and Schrödinger corresponded extensively. Both recognized that something important had disappeared from the conversation. Both saw a deterministic field equation being interpreted through a probabilistic lens. Both recognized that probability was obscuring structure rather than revealing it. Einstein's famous statement, "God does not play dice," was never an argument against mathematics. It was an argument for coherence. That was Einstein saying, "We are seeing outcomes. There is a deeper process generating them." Schrödinger agreed. "Good looking out, bro." Nearly a century later, the tension remains. The measurement problem, wave function collapse, observer paradoxes, information paradoxes, the continuing difficulty to reconcile quantum mechanics and gravity. Again and again, physics encounters puzzles that emerge when stable outcomes are treated as fundamental, and the relational dynamics generating those outcomes are pushed into the background. Phase never disappeared. It remained in the equations, it remained in interference, it remained in resonance, it remained in every standing wave. It remained in Schrödinger's mathematics from the very beginning. The deeper recognition is straightforward. The wave function evolves through phase. Quantized states arise from phase closure. Stable structures persist through admissible returns. Probability appears when measurement interfaces retain magnitude and discard phase. Our instruments are extraordinarily sensitive to magnitude. They are remarkably effective at measuring amplitude, energy, position, momentum, and intensity. They remain largely blind to phase information itself. Imagine the spokes of a bicycle wheel as a cyclist rides past. Each spoke position represents a distinct phase. Now, imagine photographing that wheel with a slow shutter speed. The wheel becomes a blur. The phase information has been smeared away. Only magnitude remains. A fast shutter reveals something entirely different. The exact orientation becomes visible. The spoke positions become addressable. The wheel was never random. The measurement lacked access to the phase information required to resolve the structure. The equations never required randomness as an ontological primitive. They required phase. This is why Schrödinger remains so important. Not because he gave us a famous dead-alive cat, because he gave us one of the cleanest mathematical descriptions of continuous relational evolution ever written. And this is precisely why a remarkable convergence is occurring today. Independent researchers working in plasma physics, self-organization, complexity science, geometry, electromagnetism, biological systems, information theory, resonance, and torsion keep arriving at the same boundary. The closer they look, the more stable objects give way to relations. The closer they look, the more structures give way to process. The closer they look, the more things give way to phase. Many recognize the traces. Some recognize the geometry. Some recognize the torsion. Some recognize the field behavior. The deeper coherence shows up when all of them are recognized as downstream expressions of a more fundamental grammar. The grammar of phase. The grammar of relation. The grammar of closure. The next step is not another particle, not another interpretation, not another layer of abstraction. The next step is recognizing what has been present from the beginning. Phase, relation, closure. The wave never stopped telling us what it was. We simply forgot how to listen. Now, we remember. The recursion holds.